So, we're building these incredible, complex AI models that are literally changing our world. But that brings up a really big question. How do we actually know we can trust them? Let's dive in and break down the quality assurance that goes into every single AI.
I mean, this is the question, right? It's the one every data scientist has to answer. After all the data, all the code, all that training, how do you prove that what you've built is actually reliable and ready for the real world?
Look, the easiest way to wrap your head around this is to think of it as quality assurance, or QA, but for AI. It's a lot like testing any other piece of tech. But yeah, it's got its own unique twists. We've got to know if it's giving us the results we expect, how often it gets things right, and just as important, how and when it gets things wrong.
And that leads us right into the first huge hurdle in AI QA, something I like to call the Goldilocks problem. The goal here is to make a model that isn't too simple and isn't too complicated. It has to be just right.
So let's break down the two big ways a model can go wrong. On one side, you've got underfitting. Think of this like a gigantic, loose, one-size-fits-all t-shirt. It's so baggy in general that it doesn't really fit anyone well. Then, on the other extreme, you've got overfitting. This is like a shirt that's been custom molded to fit one person's body perfectly. It fits them like a glove, but try putting it on anyone else? No way. Okay, so let's tie that analogy back to the real technical terms. That loose shirt, underfitting, that's caused by high bias. It basically means the model's way too simple. It's making broad, faulty assumptions and just completely missing the important details in the data. And the molded shirt, overfitting, that's caused by high variance. In this case, the model is too sensitive. It doesn't just learn the patterns, it learns all the random noise in the training data too. So when you show it something new, it just gets confused.
So you see, data scientists are walking this tightrope, right? They're in this constant balancing act. The million-dollar question is, how do they manage this trade-off between bias and variance to find that just right Goldilocks fit?
Well, the solution is a really careful, step-by-step process of tuning. You can think of it like a master mechanic fine-tuning a high-performance engine, using a very specific set of tools. So let's pop the hood and look inside that toolkit. For the most part, the process looks like this. First, you split up your data. You can't use all of it for training, so you make separate piles for training, for validating, and for a final test. Then you train the model on that training data. Now, step 3 is absolutely crucial. You validate its performance on data it has never seen before, and you tune it. And finally, you unleash it on that last pile of data, the test set, for its final, unbiased report card. Now, the real magic here, the key to all this tuning, is something called hyperparameters. These aren't things the model learns on its own. Nope. These are the settings the data scientist chooses before the training even starts. You can literally think of them as the knobs and dials on the algorithm that control how it learns, which directly affects that balance between being too simple or way too complex. And that's the whole game. Right there. That's the ultimate goal of all that hard work. All that adjusting of those hyperparameters. It's all about finding that perfect sweet spot, balancing bias and variance, so you get a model that works great on new, real-world data. All right, so we've spent all this time tuning the model. Now what? How do we actually grade its performance? How do we build a report card that tells us exactly how well it's doing its job? Let's use a classic, and honestly, a pretty funny example to make this super clear. Let's pretend we've built an app that identifies food, and its one and only job is to answer a simple question. Is this a hot dog, or is this not a hot dog? Okay, first up, the best case scenario, a true positive. The model sees a picture of a hot dog, it says hot dog, and bam, it's correct. A+, perfect score. Then you've got the false positive. This is a super common mistake. The model looks at a picture of, I don't know, a taco, and confidently yells, hot dog. It made a positive ID, but it was false. Whoops. A true negative is also a win, by the way. The model sees that taco and correctly says, hey, that's not a hot dog. Getting the rejections right is just as important as getting the identifications right. And finally, we have the false negative. This is the other big type of error. The model is shown a picture of a real, genuine hot dog, and it misses it. It says, not a hot dog. This is the one that got away. Okay, so those 4 things we just talked about, true positive, true negative, false negative, they are the building blocks for the model's actual report card. Accuracy is the simplest metric. It just tells you the percentage it got right overall. But to get a real understanding, we look at precision and recall.
Precision asks, of all the times we cried hot dog, how often were we right? Recall asks, of all the actual hot dogs in the world, how many did we successfully find? And then the F1 score, that's just a clever way to blend both of those into one single powerful number.
But here's the thing. A model can have a fantastic F1 score, a straight A report card, and still not be ready. And that's because the numbers are only half the story. It still has to pass the real-world test. Which leads us to a really important question. Is a high accuracy score on some test data really enough to deploy a model into a hospital or your bank or your phone? And the answer, almost always, is a hard no. You have got to evaluate it against business goals or KPIs. You have to ask the tough questions. Does this model actually provide the business benefit we built it for? Is it really better than what we were doing before? And this one's huge. Is the error rate acceptable for this specific business problem? An error that's totally fine for recommending a movie could be absolutely catastrophic in a self-driving car. Context is everything. And it's not just about the business side. You've also got the technology KPIs. A brilliant model is totally useless if it's too big to fit on a server, or if it's too slow to give you an answer when you need it. Practical things like how much memory it needs or how fast it can make a prediction, they are just as important as its accuracy, because an answer that arrives too late might as well be a wrong answer.
So there you have it. We've gone from the Goldilocks problem of finding that just right fit to creating a detailed report card with things like precision and recall, and finally to making sure it passes the real-world tests of business value and technical performance. That is how we know an AI model truly works. It's a tough, rigorous process. Which leaves me with one final thought for you. The next time you use an AI for anything, take a second and ask yourself, what do you think was on its report card?